Any question? All the different derivatives. Today we're going to discuss what applications we have for those. In this section, section 4, we're looking at derivatives as a rate of change. It's always been a rate of change. What's another name for rate of change? Slope. A slope, by definition, is a rate of change. So this is now we're looking at derivatives as rate of change. But it's more to it than slope. What we're going to look at here is the basic definitions of position function, velocity, acceleration, and something called a jerk. So, I'm going to start. In physics, we use the terms position, velocity, and acceleration to define a moving object. This is usually done in linear fashion. In other words, now, what do you think the differences are between each of these? There's also another one. We're also going to talk about something called the jerk. And they all have to do with each other. And they all have to do with derivatives and rate of change. Instantaneous rate of change. With respect to, I'll start writing that from now on. With respect to time t and location x at x sub 0 to x sub 0 plus, I'll call it h. H will also be defined as the difference. Are you all familiar with the delta function? What do you think that means? The change of x. Yeah, we'll use a delta function a lot, a delta symbol a lot in this course. So the instantaneous rate of change of an object with respect to time t and location x at x sub 0 to x sub 0 plus h is defined as first derivative of the function at x sub 0, which is the limit as h goes to 0, x sub 0 plus h minus f of x sub 0. Why do you think it's from x sub 0? What's that? It's a starting point, yes. Do you always have to take the starting point from x sub 0? You can take it along the trajectory or the path at any instantaneous time, x. So here's an example. The area of a circle is given by the function a equals pi over 4 times d squared, where d, what do you think d equals? Because as the circle grows or constricts, what's the only thing really changes in that picture? Diameter. The radius, the diameter, and then that, from there, it incorporates the circumference and the area. So as the area changes, so does everything else. And so that's what we're looking at. So we're using the diameter. How fast has the area A of the circle with respect to the diameter D? How fast has the area? When D equals 10 meters. The area of the circle is given by the function A equals pi over 4 d squared, where d is diameter. How fast does the area of the circle with respect to the diameter has a change when d is equal to 10 meters? So what do you think we have to do here? We're looking for a change, aren't we? You're saying how fast has it changed? Or is it? So isn't that the instantaneous rate of change? We're looking at this instant. So what does this tell us to do with this? This equation here, right? What's that one? This is called the difference quotient. When you put the limit in front of it, what's it called? Derivative. So in order to find the instantaneous rate of change, we have to find the derivative of the function. What function? That one. So A equals pi over 4 d squared. We need to know what is A prime. What's the rate of change? Look at the statement here. What is it changing with respect to what? Diameter. So this function should have been A of D What does this actually tell us here? It tells us our function name. This is the area function. The variable we're interested in is the diameter. So when we take the derivative of it, we're actually taking the derivative with respect to the diameter. We're taking the derivative of the area with respect to diameter. So what is it going to become? Using our shortcuts from last class. Very good. Both of y'all right. Yes. The first step, because we're looking at this is our independent variable, the power comes down. So we have pi over 4, which is a constant, 2d, that's the derivative of d squared. 2 and the 4 cancel. So our function is pi d over 2. That's our rate of change. What is our rate of change? Give me a number. Half pi. Very good. Oh, because it changes it from 5 pi to something like 15 point whatever. So it does change it. If we look at it, our derivative was pi over 2d. When d equals 10, pi over 2 times 10, those two cancel. So our instantaneous rate of change is 5 pi. 15.6 something. In physics, in engineering, in motion problems, are we done? What's missing? What unit do we have? In meters. So the units are in what? Meters. So far so good? Motion along a line displacement velocity acceleration jerk. These are the things we could find with a derivative. What's the difference of them? What's the difference between these? I know you've heard them all before. You've heard velocity before. You've heard acceleration before. What do they mean? How are they related?
Velocity does something with miles.
What if you're only going 6 inches? What if you're an ant? So you can only track them if they're going miles per second? It's over some unit of time, yes. These all have to do with the position of a function and the rate of change of that object through some delta t. Speed is the displacement of an object. What does that mean? From x sub 0 to x sub 0 plus h. That's the distance it traveled in some time period t. So speed is how far you traveled over a certain time period. That's speed, displacement. You've moved from point to point. That'll be our original function that we'll be dealing with. It tells us our position of the object after t units. Displacement of this object. T plus delta t minus f of t. What does this mean? Let me write it. What does that mean? F of t plus delta t minus f of t. What does that mean? What does t represent?
Time.
Okay. What does delta t?
Change of time.
So it's as similar as h. This is my displacement. I changed from one position to another position. Because it all has to do with time. What is velocity? Change of displacement over unit time. The average velocity noted by VAC displacement over time. Which is the change of x over change of time, which is equal to f of t plus delta t minus f of t all over delta t. Is that a derivative or not? It's an equation, yes. Not a derivative is because derivatives have the limit function as the change h goes to 0. This is simply two positions over a certain time period. That's all it's telling us. Now we could use that to define the velocity is the independent instantaneous rate of change is also instantaneous rate of change of the displacement with respect to t. Instantaneous rate of change of the function is the displacement with respect to time t. S equals f, or S of t is equal to f of t. Then the object velocity with respect to time is the velocity of time equals ds dt, which is the limit as t goes to 0, f of e plus delta t. So the velocity is the displacement of time, displacement over time is the, basically it says it's the derivative of speed, of your displacement. What does this stuff here mean? If I just gave you this, v of t ds dt, what does that mean? That's a whole sentence in itself. What's that? Exactly. Well, not over time. It's with respect to time. So it says velocity is a function with respect to time is equal to the derivative of speed with respect to time. So it would be s prime of t. And that's what this defines. I don't want to get too convoluted here. If the limit was in there, remember this function here, f of t plus delta t minus f of t over delta t, that's your displacement, that's your s. When I put the limit in front of it, it now becomes the derivative of that s. Speed is actually the absolute value of velocity. Now we've just differentiated between speed and displacement. Displacement is the position of a body from one point to another point with respect to time. Speed is the absolute value of the velocity, which becomes the absolute value of ds dt, which is the absolute value of the displacement function. All of these things mean the same thing. Any questions so far? Because I'm gonna have them for you in a second. It'll be a problem. Okay, then after velocity comes what? Acceleration. So velocity is a change of displacement. What do you think acceleration is? Change of velocity. Is the derivative of my velocity function with respect to time t. So that's the informal definition of acceleration. It's the derivative of velocity function with respect to t. If an object's position at time t if the object's position at time t is s of f of x, ft, then the object's acceleration at time t is aft. What do you think that equals? If an object's position at time t is s of ft, then the object's acceleration at time t is what? Look at the definition of acceleration, the derivative of v. So it's going to equal to what? Nothing. How is it related back to our displacement function? Very good, yes. If the acceleration is the first derivative of velocity, and velocity is the first derivative of displacement, therefore the acceleration is the second derivative of your displacement. For example here. Everybody follow this. The function s equals 1/2 gt squared. This is the displacement, the position function of a falling object. What is g? Gravity. Is it a constant? What is its value? .2 meters per second squared, or is it 9.8? Maybe 9.8 or it's 16.2 feet per second squared. What exactly is gravity? How would you define it? With the three terms that we used, or we defined: displacement, velocity, acceleration. What is gravity? It's negative velocity. No. You could look at it, but if we're talking about gravity, it's always going down, so that's the only direction it has. That's why we take it the absolute value. But why does it say second squared? Exactly. Gravity is the acceleration with respect to time t. And later on we'll talk about the universal gravitational constant. That's the universal, but we'll talk about this when we do some other examples. The gravity of any objects in space is given by this. The universal constant, that's that little g in there, mass of the two objects, difference of the two objects, divided by the radius squared. Gravity is a force, acts on everything. Despite what you remember watching on space movies, if there were two space people, astronauts, yards apart, with no jetpack, no anything, can they get to each other? Or will they ever get to each other? ¿Por qué no? Why not? Gravity in space is 6.2 times 10 to the negative, I think it's negative 20. There is a force of gravity in space. Everything exerts a force. Anything with a mass exerts a force. So yes, these two astronauts, I even put them at 10 feet apart. They would eventually attract each other. Of course, they'd be dead and their bodies decayed. It would take a couple of thousands and thousands of years. But their bodies, because the astronauts are closer to each other, so the gravitational acceleration of these two astronauts is greater than the planet to the nearest astronaut. There's a point in which the distance is so great that these two people being 10 feet apart, its gravitational acceleration to the two is greater than the gravitational acceleration from this astronaut to the body of in space, this planet. I've ever taken a physics course. Take a college physics course. It is so fascinating what's out there and how the whole universe works. My first degree, my first major when I was in Europe was astrophysics, of how galaxies move weightless in space. Anyway, so find me both of these values. And my displacement is half gt squared. Find me the velocity of the object, and then find me the acceleration of the object. So what's the velocity? Look at here. Inside the parentheses, it tells you what variable you're taking the derivative of. So in other words, in this function, do I do anything with the 1/2? How about the g? Because the only thing I'm interested in is t. So for this case, this part is a constant. It doesn't do anything for me. So I take the derivative of t squared, which becomes what? 2t. The 2's cancel, so my velocity is simply gravity times time. So what's the acceleration? This is a constant. So I'm going to take a derivative of t. The derivative of t is 1. So the only acceleration we have is thanks to gravity. Anybody ever hear of those experiments done by Galileo and Michelangelo and all those other scientists of the past? That if you drop 10 pounds of leaves and 10 pounds of concrete, which one hit the ground first? Or even duck feathers. I use duck feathers, what they did. 10 pounds of duck feathers or 10 pounds of brick. Which one hit the ground first?
Oh,
They both hit the ground first?
yeah, because both the same time at the same time.
Or at the same time? Yes, they would hit the ground at the same time because it's the mass that matters. And that's that. In the Leaning Tower of Pisa, I don't know if you've ever been to Italy and seen what the Leaning Tower of Pisa, it's actually a cylinder. It's hollow on the inside. And what the scientists used to do is go in there and just drop things. The reason for that is because there's very little air disturbance, wind or anything like that. You just have the air, yes. But if you drop these objects and they fall on the ground at the same time. So yeah, if objects are the same weight, doesn't matter the size or the shape, they'll fall at the same rate. They'll fall at this rate, gravity. All right, let's look at an example here. Ooh, hold on. I forgot one other thing. Rate of change, instantaneous rate of change of the acceleration function. And that's what you call a jerk. Yes, that's a legitimate term. This is a jerk. So the derivative of acceleration over derivative of time, with respect to time, is actually the second derivative of velocity or the third derivative of your displacement. All of these mean the same thing. Remember last class we talked about the different ways you can write derivative. Okay. Then with our example up here, we had the position function, the displacement function, 1/2 gt squared. Velocity was gt, acceleration was g. What is the j of t of this function? Why? Yeah, because g is a constant. The derivative of a constant is 0. Okay. Here's an example. We're going to get 2 examples and call it a day. This is about a falling object. A ball is dropped from a high cliff. The important part. A. Meters will the ball drop in the first 3 seconds? That's the first question. How many meters will the ball drop in the first 3 seconds? Second will be, what is the velocity of the ball at that time? And C, what is the acceleration of the ball t equals 3 seconds? What is the acceleration of the ball at t equals 3 seconds? So what formula do we use here? It's a falling object. When you say falling object, what does that mean? At time 0 equals 0, does it have a initial velocity? No, because if you drop it, you have to hold the ball first, and then you let go of it. Then it starts from there. So when you say dropped, everything at the initial point, time 0 and velocity or acceleration, all that stuff is 0. Since it's a moving object, what formula do we use? We use that equation. What's G going to be? What's that? No. Y. Very good. Because we're using meters, we have to use 9.8 meters per second squared. Very good. The clues are in the sentences given to you. A. How do we find A? Distance traveled. Time 3 seconds. How do we find that? Very good. Just plug in 3 into our function. 1/2 9.8 times 3 squared. Half of 9.8 is what? 4.9. 4.9 times 9 6. It traveled 44.1 meters. Tell me the velocity. Yes. We use 16.2 if it's in feet. And typically in physics and engineering worldwide, you use what's called the MKS, meters, kilograms, seconds. We're the only country that uses feet and inches. Ships and planes still fly. So how do we do this? What's the velocity function? How do we find velocity? Well, we take the derivative of your displacement function. Velocity is the ds over dt. What's the derivative of our s function? GT. We just did that about 10 minutes ago. So after 3 seconds, what's our velocity? Gravity is 9.8 meters per second squared, so it's 9.8. Time is 3. 3 times 8 is 24. 3 times 9 is 27. 29.4 meters per second. Is it meters per second? Gravity, what's the units in gravity? 9.8 what? Meters per second squared. 3, its units are in seconds. One of the s's. So it's meters over second. And I guarantee you, that's going to be the most difficult part of this section when you do homework, is going to be the units. We pick out the numbers pretty quick. Well, it's wrong because your units are all wrong. Find the acceleration. What's the acceleration? Very good. Which is what? 9.8 what? Very good. Yes. Because velocity was g times t, the derivative of velocity would simply be g, so it's just gravity. So that's why they say, if you ever drop an object, the only force acting upon it is gravity. That's its only acceleration. Let's take another example. A dynamite blast flows a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a maximum height, or a height, S equals 160. S equals 160 t minus 16 t squared. Reaches a height of S equals 160 feet minus 16 t square feet in t seconds. What's the difference between this one and the last one we just did? That's t. Direction is this one going? Going up with the initial velocity from the blast. So you have two diopposing forces acting upon it. You always have gravity acting upon it, but you also have the initial velocity of the blast, which is why you have all this stuff. The negative 16t squared, if we just had that, wouldn't that be our function for gravity t squared? This is our initial velocity. A. How high does the rock reach? What height? What are the velocity and speed of the rock when it is 256 feet? Way up on its way down. Will they both be the same? Will the velocities going up and down be the same? Think about it. Will they be the same? An object going up versus an object going down. Why not? That? Yes, gravity will be constant. When it goes up, you're right. Gravity is a constant force acting upon the object going up. So every second it travels, gravity's taking a larger effect on it. Eventually, what happens to the rock? It slows down. Eventually, it reaches the vertex, the apex of the curve. Then it comes down. So in other words, from the moment the explosion happens, that rock is losing speed going up. On the way down, it's the opposite. Once it reaches its vertex, its velocity up there is what? 0. But from there, gravity accelerates it all the way down to its ground. So it's always an increasing function now. So it'll get bigger and bigger and bigger, starting from 0. So that's why it's both going up and going down. We look at different answers, depending on its vertex. Let's see what number C is. Oh. What is the acceleration of the rock at any time t? During its flight. And when does the rock hit the ground? When it hits the ground, what's happening there? Goes instantaneously to 0, right? How do we know how high it goes? We discussed it earlier. We know how high it goes by how long it takes till the velocity of the object going up reaches what? 0. Or the acceleration, yeah, so we have to look at all these things. So let's go ahead and solve these. So let's look at A. How high does the rock reach? We have the formula right here. So how do we solve that? How do we find the value, the height value? It's the only variable we have in our function. Is there a way we can figure out how to get the time? Just talked about it a second ago. If we knew, because we're looking at how high it goes, if we knew how many seconds it took to get that high, you can tell me how high it is. How do we figure out how many seconds it took to get that high? Just talked about it a second ago. Yes. Find how long it takes for the velocity to go to 0. So, that's step 1. Position function is 160t minus 16t squared. So the first thing we have to do is find the velocity function. The velocity function is the same thing as what? First derivative of the position function, the displacement function. So we got to take the derivative of this, which would give us what? What's the derivative of our position function? Since this is subtraction, the derivative of this part is just 160. What's the derivative of this part? 32t. Then what do? You have to know how long it took to get to the highest point. How do you solve for t? What do you have to do first? Yep. Set the velocity equal to 0. So we have 160 minus 32t equals 0. Now you have to solve for t. $32 to both sides. If you subtract 160, you get two negative numbers. You could do that, it doesn't matter. But it's much easier if you just leave it like this first. And divide by 32. $160 divided by 32. Right. So it takes 5 seconds after the initial blast to reach its highest point. How high did it get? Where do we put this function? It is t. What function deals with position? The displacement. It tells you the position function. So plug that in there. So we have S at 5 equals 160 times 5 minus 16, 5 squared. $800, 16 times 25. $800 minus 400. So it's the maximum height reached was 400 feet. What are the velocity and speed when the rock reaches 256? What is the velocity and speed when the rock is 256 feet going up and going down? Velocity, speed, at 256 feet. Up and down. How would you find this? What are the formulas you're dealing with? Well, no, for these, what's the velocity formula? What's the speed formula? I have them both here. So what is S of t? No. S of t was given. 160t minus 16t squared. What else we got to do with that now? Set it equal to what? How do we know this is going to give us two answers? It's a quadratic equation. It'll tell us at 256. So how do we solve this? What do we have to do? How do we set it up? (16t squared plus 160t minus 256 equals 0. We don't want a leading coefficient to be negative, because remember, the ball's going up. If we graph to this, like this, we can go ahead and just change these values. We can multiply the entire equation by -1. Okay? Simplify this. How do we do that? Yes, you could factor, but we're not trying to see, can you factor anything out? Do they have anything in common you can factor out? 16 goes into 16, right? One time. 16 goes into 160 how many times? 10 times. Does it go in 250? 6 times 100 is 600. Well, let's see. They all have a 2 in common, so I can divide each of these by 2. 8t squared, 80t, 125 equals 0. It made it a little bit easier. My bad. It's 256.
That's not the same.
You told me something.
So it should be 16 since they have a common.
Yeah. I'm sorry. I can factor out a 16 out of each of these. So it's t squared minus 10t
Minus
plus 16 over this function. I don't want a leading coefficient if it's negative. So, factor this one out now. What equals t squared? T times t. The second sign's a plus. What does that tell us that goes inside here? No. If it's a plus, that means they're the same sign. They're both going to be negative. What times what is 16? When you add them, you get 10. Set them both equal to 0. So these are the two times that our values will give us the height of 256. So I take both of those. I take t at 2 and t at 8 for both of those functions. So I take s of 2 and s of 8, take v of 2, take v of 8. So let's review what we just did in that question. That question was, what are the velocities and speed when the rock reaches 256 feet on the way up and down? That just tells us the height. We have to know when it gets that high. So we have to find out what is the time value to get that high. We take our function, set it equal, our velocity function, set it equal to 256, solve for t. Graphically, we know that if it goes up, it must come down. At 2 points, it has to be 256. Want me to work these out with y'all? Find those four values? S of 2 is 160 times 2 minus 16 times 2 squared. 320, 16 times 4, so S2 is 256 feet. And S8 is going to be the same thing. Now let's find the velocity at 2 and the velocity at 8 seconds. $60 minus 32t, so 160 minus 32 times 2, 160 minus 32 times 8. $160 minus 64 is 96 feet per second. V at 8. 160 minus 256. So V at 8 is negative 96. We can't use this one. So the only time that we have equals 256 is at 2 seconds. All right, what's the next question? What is the acceleration of the rock at any time t during its flight? What is the acceleration any time t? How do you find acceleration? Yep. The acceleration is simply the derivative of velocity. So the derivative of 160 minus 32t over dt is simply 160 minus 32, which is 128. Feet per second squared. No, hold it, come on. The velocity function is 160 minus 32t. The derivative of that goes to 0, is simply negative 32. The acceleration at time t is negative 32 feet per second squared. This is a constant. 160 is a constant. Why is it negative? Because of gravity, yeah. Since the acceleration is a constant function, 32, the force of gravity is it's slowing down going up, it's speeding up going down, but it's always gravity acting upon it. So its acceleration function is negative 32 feet per second squared. When does a rock hit the ground? When does a rock hit the ground? It's looking for position, isn't it? Which one of the functions deals with position? We have S of t, we have V of t, we have A of t. Which one of these deals with the object's position? S of t. That's the displacement, it's position. So S of t is 160t minus 16t squared. Where S is in feet. How many feet do we want to measure it at? 0. What can we factor out of the function? 16t gives us 10 minus t. Set both of these functions equal to 0. These are our two answers. Which one's correct? Why? Very good. 0 is where it began. T at 0, that's the beginning. That's about to go up. This one's coming back down. So the rock will hit the ground after 10 seconds. Do this next time. On Wednesday, there's one more topic we can discuss about derivatives. Okay, this is physics and engineering. We have another part on business. Marginal cost, marginal profit, marginal. Whenever you hear marginal, that means derivative of your cost function, your productivity. We'll look at that next time. How many of y'all took business courses? You see why I hesitate these. I'm an engineer. I'm a mathematician, computer engineer. Business ones, yeah, we can do them because all it is derivative. But what it means, marginal cost, marginal revenue, all this, all these different words. So, okay, everybody, we'll pick up from here and then we'll finish up section 4 and 5 next time. We're getting close to doing. I think next time we're also going to do the trig functions, which I want to leave you that before the break, so you have something fun to deal with. Hey, everybody, have a great, safe day. I'll see you all Wednesday.